Hello, welcome to another exciting episode of Fun with Physics. This is your host, Mr. Easley. For this video, I'm going to demonstrate how to do at least one of these from the wizard level. I'll work one through and also might talk through some techniques when you're dealing with this from this level, because I was looking at the wizard level and it encompasses anything that's in this level. I already did a video for the beginning ones here. If you haven't done that, you should make sure and do that first. But really, everything that is contained on this wizard level is obviously on here, and so I'll show you that. And primarily, we could be looking at, oops, wrong page. So when we're looking at here, we've already solved one similar to this. So let's just move down the row and we will briefly discuss how to solve something of this nature. To start with, we know that this column is double that column. So this would be equal to 6.24. And remember that time controls the vertical distance. So we ought to be able to find the distance to the peak fairly simply, and that's also going to help us to find the velocity. So to solve this, and we'll work through some of these, but you have to make a little bit of an assumption. We can use this distance on the x to find the horizontal, the x component of the velocity, and we'll do that, but that really doesn't help us on the y-axis. And to solve the total velocity, we're going to have to solve the x and the y. So right away, we can go ahead and solve for the velocity on the x-axis. So we know that velocity equals distance over time. This is true. We can just make those for the x component. So we can say velocity on the x-axis equals 82.4 over 6.24. That's going to equal 13.21. But that's just going to be the velocity in this scenario. That's going to be the velocity on the x-axis. And we'll use that to finish solving this, but that really won't help us too much right now to solve for the distance on the y-axis. So if we go to our equations, if we look, we have a distance on the x-axis that doesn't really help us. If we look at our equations here for acceleration, we start looking, we do have time and we have acceleration. And so if you start looking at these, a lot of these have velocity initial, velocity final. The ones that have acceleration and time, which would be these three. This one right here is actually going to be, I believe, our best bet. And that's because we can make an assumption and we have to visualize what's going on here. We need to think about starting at this point in the trajectory, coming down to here. And the reason why we can do that is we can set your velocity initial on the y-axis would be 0. So we can use this equation. And we can work this out, but we can set this initial velocity to 0 if we think about it the second half. And in other words, how far is it going to fall on the y-axis? If we set that equal to 0, that'll let that first one cancel out. And then we have time. And here's where we have to be tricky. We're just wanting this little section of time, so we want that t up. That'll be squared. So that's going to mean distance is going to equal, if you run that math, 47.70. What that tells us is this section here would be 47.70. Now, that doesn't tell us a velocity on the y-axis yet. We're going to have to jump over there and find an equation for that. But it shouldn't be too bad now that we know the distance. And so I would actually say we could probably jump and use this equation right here like we've used in the past, using this distance we just solved for. we'll use this distance in this equation because we're trying to find out the initial velocity on the x-axis. And so we can say 47. Here we can say it really actually doesn't matter because we know that the velocity on the y-axis is just equal in size but opposite in direction. You could think about it, you could call one original, one final. I would say probably let's just try to stick with the convention, and we'll call the initial as we're taking off here as our unknown and the final to be 0. And our time again, we want to use that time just for half of the trajectory to get to that point. So we end up with there. We'll multiply both sides by 2. And so we'll find here that our velocity original would be 30.576. And this is going to need to be clarified. That is on the y-axis. Because remember, time, and in this case, we're trying to think about things on the y-axis. And really, you're the person that will be thinking about, are you working on the y-axis or are you working on the x-axis? And on the y-axis, there's always that acceleration component due to gravity. You can think about these two components as different. We can bring them together at this point, though, because we do have a velocity on the x-axis here and a velocity on the y-axis here, and we can solve that to find the total velocity. And so on the x-axis, you can't see where I'm working, I apologize. The velocity on the x is equal to what we found over here, 13.4. And then the velocity on the y is what we just found, to be equal to 30.576. 30.576. And so this essentially makes a right triangle. Should be sort of familiar with this by now. So we'll say, well, what is this? This is our resulting component. And we're going to use the Pythagorean theorem to solve that. And we're going to get our solution to be 33.38 would be this unknown side here. And that is going to be the magnitude of our vector right here. Final thing to solve for this angle, of course, we just need to solve for this angle here. Lots of ways you can do it. I am just going to stick with the good old equation. We'll use one of these so we can say velocity on the y-axis equals velocity resultant, which is our actual initial velocity of the combined multiplied times the sine of theta. So here we have velocity on the y, which is 30.576 equals 33.38 sine theta. And so we're going to get an angle over here of 66.33 degrees equals theta. That means that would go there, and then this would be 66.33 degrees would be our angle. This one is Not super easy. You got to make that connection of thinking about inverting that. One like this is almost identical, except I don't think I'm going to work through an example here unless I end up having a lot of folks needing it. I will say if you encounter one that just has the distance to the peak, what you can do is you can use this exact same equation, and instead of solving for distance, since you have the distance, you can use this exact same equation and you could plug in your time component there. So it would, sorry, not your time component. You would plug in that distance. So on this one, it would look something like, and we would assume again a zero because we would think about it going from the top down. So we'd say zero, and here we're actually solving for time. So in this scenario, you would just solve for the unknown of t. That time you would get would be this partial time because you're actually thinking about just half of this scenario because you're assuming a y velocity on the y-axis of 0 is starting at the top. Then, of course, you could find total time. And then once you had that, you would do the exact same process you used here. Once you had these done, you would have these done to solve for these two. So that would finish figuring out this one. And then we already showed how to do one such as this. I'm going to walk through doing right here. I'm going to make this one pretty quick at the beginning because we've sort of already started this. We would use the same equation that I just discussed right here as we would try to do this for this next column. So we'd say distance equals velocity of initial or original times time plus 1/2 at squared. As discussed before, we'll use this distance. We'll assume a velocity of 0 because we're starting at the top. Gravity, of course, is negative 9.8. At this point, I will solve for t. And so I realized as I was doing this with this negative 9.8, since I'm calling acceleration down, this displacement is actually, in fact, in a negative direction. I probably should have shown that earlier to keep consistent with my signs. But this would solve out to be 3.388 is going to be t squared. So time is going to be 1.84. Once again, this time would represent the half time, which is the time to up, so that we would put 1.84 there. .68 there.